All right, so we saw in our last class that we solved for the energy levels inside an infinite well, namely one where the potential barriers on either side of the well go to infinity. So the particle, once it gets inside this well, is trapped and it can't get out. We found these discrete energy levels as shown here, where E1 infinity again is as shown. Just recapping quickly from what we found for the so-called infinite well. Here were the actual wave functions themselves, and we solved the time-independent Schrodinger equation. So n equal 1 was a symmetric case, n equal 2 anti-symmetric, n equal 3 symmetric, and so on and so forth. We also found, though, that in the design of lasers, we are not satisfied. It's not a good idea to restrict our attention to V equal infinity, the potential boundary equal to infinity, because real devices don't do that. We found that when we take, for example, a heterojunction, two junctions between aluminum gallium arsenide and gallium arsenide, and then again gallium arsenide and aluminum gallium arsenide, that we do indeed form a well, but the depth of that well is finite. It is not infinite. So part of the design of making a good laser is ensuring that particles are well trapped inside this well, which means that the well has to be deep enough. And so we're going to need to look at that, but that also means that we have to solve the case of Schrodinger's equation for a finite potential well as opposed to the infinite potential well that we just looked at. And that was where pretty much we left off. This was the oops, mouse is very sensitive here. This is the time-independent Schrodinger equation, which I say we have to write in, which we have to solve in three regions. I rewrote it a little bit here to make it just to look a little bit more like a normal differential equation, so to speak. You'll notice that for inside the well in region 2, V is equal to 0, right? So this is 2me over h bar squared. You might recall that 2me over h bar squared is k squared, so that makes things a little bit easier to write. This is d2 phi dx squared plus k squared plus k squared phi is equal to 0. That's the standard harmonic oscillator. Solutions are cosines and sines, cosine kx, sine kx. Once again, we could identify a symmetric solution and an anti-symmetric solution. Okay. How about in regions 1 and 3? Before, with the infinite well, when V0 was infinity, it would be, of course, impossible for the electron to get, or the particle, to gain sufficient energy to cross that boundary. That's the idea of an infinite energy boundary. It is truly trapped inside region 2. So we were able to set the wave function in region 1 and region 3 equal to 0. Well, clearly that's no longer the case. Now with a finite energy boundary, it is possible for the particle to gain sufficient energy and hence find it in region 1 or region 3. You'll notice that what are we looking for? We're looking for energy levels. They're going to be discrete, as we'll find out. We don't know that yet, but we'll see they are still going to be discrete. And we're looking for energy levels inside region 2, inside the well, right? So any energy level inside the well clearly is going to be less than V0. Right? So this term E minus V0 will always be a negative number for the solutions we're looking for, right? So in region 1 and in region 3, where V is equal to V0, E minus V0 is negative. That flips this sign, and when you flip the sign of this same differential equation, the solutions go from cosine and sine to a pair of exponentials, e to the plus, I'm calling it gamma x, and e to the minus gamma x. But we can't keep increasing exponentials. Again, what does phi represent? Its magnitude squared is the probability of finding the particle at that particular value of x. If we had an increasing exponential out here, it doesn't make any sense to say that the probability is going to probability density is going to infinity as x. So we need decaying exponentials here. The farther we get away, the farther out in x we go, the less likely it is of finding that particle. So we need exponential decay in both regions. So for region 3, where x is bigger than d over 2, I would simply write it as e to the minus gamma x. And for region 1, where x is negative to have exponential decay, I would write it as e to the plus gamma x. And gamma is simply this constant flipped. Instead of e minus v0, v0 minus e to make it positive, and I'm giving that the name gamma squared. Okay, so this is the equation we need to solve. An important consequence of Schrodinger's equation, really a postulate of quantum mechanics, is that the wave function phi and its first derivative are continuous at a boundary. That's a postulate. That means much of quantum mechanics is axiomatic. We accept this as being true. More depth on that, of course, in a real quantum mechanics course, which this is not. This is doing, as I said, just in time quantum mechanics, so we can move on for what we need to know with lasers. But let's just accept these boundary conditions. We have to apply them at x equal plus and minus d over 2. You'll find that you get the same answer at x equal plus d over 2 as you do for x equal minus d over 2. So we only need to consider one. Convince yourself of that if you don't see it. We'll look at for the symmetric case. Continuity at x equals d over 2 says that phi 2 of x has to equal phi 3 of x at x equal d over 2. Okay? And we also have to have the case that the derivative of phi 2 has to equal the derivative of phi 3, again at x equal d over 2. That'll give us this equation by just simply differentiating the functions on the previous page, right? Now divide these two, divide this by this, divide this by this, and here's the equation we get. Simplify it a little bit. In other words, cosine over sine is cotangent. Take the reciprocal, you get k tangent kd over 2 is equal to gamma. That's the what we would call the eigenvalue equation that gives us the energy E. We're looking at the symmetric case. I'll let you go ahead and try it for the antisymmetric case, just to make sure. You should do it to make sure you understand it. But for the antisymmetric case, you get similar but a little bit different. K cotangent kd over 2 is equal to gamma. And what most people do is use the identity that the cotangent of x is the tangent of x minus pi over 2, and that's what I did, and write it that way. So here, as summary, we solve for the energy levels for the symmetric case via this equation, for the anti-symmetric case being this equation, and you're saying energy levels. What energy levels? Well, the energy we're looking for is the energy E, which of course is buried in these equations in the K and in the gamma, because K squared has the energy that we're looking for in it, and so does gamma squared have the energy that we're looking for buried in it. Now you'll notice that K, in both cases, K appears inside the tangent function as well as outside the tangent function. That makes this a transcendental equation which cannot be solved algebraically. It must be solved numerically. Also, oops, what happened there? Also, generally when you have equations of this form, a trigonometric equation with K inside and outside, the solutions for that will in general be discrete solutions. So, okay, we said that the energy levels are going to be discrete. It looks, based on the form of the equations, like they will be. So how do we go about solving these equations? Well, again, as a reminder, for the case of the infinite well, when v0 equals infinity, the wave function goes to 0 at the boundaries, and what we found was that kd over 2 was an integer multiple of pi over 2. When where n are called quantum numbers, and n was odd for the symmetric wave function, n was even for the anti-symmetric wave function, and again the discrete energy levels that we solved for were given by, well, you recall what we did. That was relatively simple, right? It was given by the expression shown here. For a finite well, based on the form of the equations, we see that the energy levels still are going to be discrete, but for the finite well, the quantum numbers are no longer integers. They are real numbers, okay? Real numbers now, no longer integers. And I'll give them a name. I'll still call them n, but I'll call them nQW for n quantum well. So they're found as follows. We have to, again, the name of the game here is to try to systematically solve these two equations to find the energy E. That's the name of the game. What is the energy level E? It's going to be discrete. You have to solve these equations numerically, and you have to get it. So what I'm going to do is do the following. Again, I put on the side here the results for the infinite well just so you could see the correspondence. For the infinite well, where n was a pure integer, right? Pure integer? Is there such a thing as an integer, okay? Kd over 2 was an integer n times pi over 2. Well, here I'm going to let Kd over 2 equal to a number now, no longer an integer. I'm going to call nQW for n quantum well times pi over 2. So it looks very, very similar, okay? The energy levels I'm looking for are going to be discrete, so I'll label them as such. I'll call them E sub n. And here was the case for the infinite well. E sub n was n squared times E1 infinity. Let me do the same thing or a similar thing here. Instead of, En is n squared times E1 infinity, but instead of the integer n squared, I'm going to put n quantum well squared. So that means this quantity n quantum well that I'll be looking for, I'll be solving for this. I'm going to solve my equations for this n quantum well, because once I have that, n quantum well, you see, is simply the square root of E sub n over E sub 1 for the infinite well. So once I know this, of course, I know this is what I want. Remember what k squared and gamma squared were. So let me do let me do the following. Let me define a quantity n max, which is V0 over E1 infinity. If I do that, then I could write gamma squared as, okay, I could simplify the writing of this a little bit, okay? I could write gamma squared as n max squared minus n quantum well squared over n quantum well squared. So, with that in mind, I could take, let's say for the symmetric case, I could take my characteristic equation, my eigenvalue equation, and remember what I said. I said I'm going to write k d over 2 as n quantum well pi over 2. So kind of very similar to what we saw for the infinite well case. I have gamma, which I just showed you how to write here by defining this term, which I'm simply calling n max. Okay, n max is V0. This assumes something, by the way. Let me just make sure everybody is clear. It assumes we know E1 infinity, but we probably do. Again, how would we get E1 infinity? Well, we'd have to know the width of our well, which, that could be a design parameter. Indeed, it often is. Because if you change the width of the well, you change the frequency at which the laser will laze, but that's okay. Let's assume we know the width of the well, or we're going to use that as a design parameter or whatever. The mass, that would be the effective mass of the particle. So if we were in the conduction band, that would be the effective mass of the electron in the conduction band. If we were concerning ourselves with the valence band, that would be the effective mass of a hole in the valence band. Usually in the laser business, if you do a good job designing the conduction band, the valence band takes care of itself, and that's pretty much what we're going to do. We'll design properly a laser for a deep enough well in the conduction band, and we'll talk more about that as we go on. I'll show you more specific results on that. So in other words, I know n max. It's something I know because I'm assuming I know the depth of the well, V0, that's given somehow. In your homework, you'll see if you've looked at it, I tell you 166 millielectron volts is what V0 is to do your homework. And then I'll show you how I even got that, okay? And E1 infinity, if we know the width of the well and the effective mass, we could compute that too. So this is a known number. N max is something I know, okay? What I don't know is n quantum well. That's what I'm looking for. So what I'm trying to do is express everything in terms of kind of one unknown, and when the one unknown I'm going to pick is n quantum well, because once I know n quantum well, I know I know how to get the thing I'm looking for, which really is the energy level, the discrete energy level in the well from this equation. Okay, so I could rewrite these equations then as, you know, so instead of putting the k here, I wrote it as gamma over k. So I could take my gamma over k, and you see I could write it like that. And then for the antisymmetric case, I could write this equation as shown here. The right-hand side is the same in both cases. Where again, I'm reminding you that n max squared is v0 over E1 infinity, and I'm assuming I know that number. And n quantum well, I don't know. It's what I'm looking for. It's the variable I'm solving for, because once I know it, I know the real thing I'm looking for. The real thing I'm looking for is E sub n, the energy level in the well. So you see, look at either of these equations. I know n max. I don't know n quantum well. Even here, I know n max. So you have to solve each of these equations numerically and determine what n quantum well is. And that's what we'll run through now, and I'll do an example, and for homework you'll have to slog through all this yourself. So let's look at the symmetric. Well, let's look at both cases at the same time, and I want you to notice my labeling. Here's the symmetric case for the eigenvalue equation. Here's the eigenvalue equation for the anti-symmetric case. What does that tangent function look like? I don't know n quantum well, but whatever it's going to look like, if I just make a plot for myself of the left-hand side and the right-hand side, okay, as a function, I'm going to let n quantum well go from 0 through, looks like I'm going up to 4 here. I'm going to make a plot, okay? So as n quantum well goes from 0 through 4, the tangent function, and I'm only showing the first quadrant here because all the numbers we're looking for are positive. We don't get any negative numbers, so there's no need to look anywhere else, right? As I vary n quantum well from 0 through 4, the first branch of the tangent function is this, okay? Then now the next branch of the tangent function is going to correspond to this guy, because this is n equal 1, that's the symmetric case. This is going to be n equal 2, that's the anti-symmetric case. N equal 3 is going to go back to the symmetric case, so that's this branch of the tangent function. N equal 4 is going to go back to the anti-symmetric case, which is here. So I'm trying to color code these things for you a little bit. So this is, when I say left-hand side symmetric, left-hand side anti-symmetric, I'm just drawing the red one here, tangent n quantum well, pi over 2, as n quantum well ranges from 0 to 4, and I get this curve. And then for the anti-symmetric case, n quantum well pi, tangent of n quantum well pi over 2 minus pi over 2, as n quantum well ranges from 0 to 4, I get the blue curves here. Okay, so that's the left-hand side of the equation. That has to equal the right-hand side. Well, the right-hand side has an additional term in it. It has n max. N max, remember, look back, what was n max? N max squared was v0 over E1 infinity. So it's telling me something about how deep the well is compared to E1 infinity, okay? But it's a number that I know. So let me just pick some numbers. If I picked for n max, you know, again, n quantum well is the variable, so I'm going to now plot the right-hand side of the equation as a function of n quantum well. If I picked n max equal to 1, I would get, do I even see it here? Yeah, here it is, right here. I can't see my own. I'd get, you know, you can see at n quantum well equals 0 goes to infinity, okay? And then it falls back down, and it stops at 1 because I picked n max at 1. You notice that as soon as n quantum well gets bigger than 1, this term goes imaginary, and that we excluded at that point. So if I picked n max equal to 1, there's the right-hand side of the equation. If I picked n max equal to 3, I get this blue one here. If I picked n max equal 10, I get the purple one. If I picked n max equal to 30, I get the green one here. Where are my solutions? Well, my solutions are the intersection of the left-hand side with the right-hand side. So, for example, for n equal 1, I get one solution. Right here, where these two guys intersect, right? That's saying there's one energy level in the well for n equal 1. And that value of n, that n quantum well that I'm looking for is going to come directly from here, and we'll see. We have to solve this numerically for this root. We have to find out what, when I pick n equal to 1, what value of n quantum well will make the two sides of the equation equal. Okay? If I picked n max equal to 3, you'll notice I get 1, 2, 3 solutions. So I get a symmetric, I get an anti-symmetric, and another symmetric. If I pick n max equal to 10, I get a solution here, a solution here, a solution here, and a solution here, and onwards, right? If I pick n max equal to 30, I get a solution here, a solution here, a solution here. It looks like it goes on. I may get more solutions, but I'm out of my plot here. But you get the idea. So what you need to do is numerically track, pick one branch of the tangent function. Okay, let's say you pick the n equal 1 branch of the tangent function. That's this red curve, right? Let n max vary from, let's say, 1 up until whatever, you know, the maximum it could be, and well, the maximum it could be is dictated by this, because n quantum well has to be smaller than n max, otherwise this term goes imaginary and I'm done. And you see that in each case, right? For n max equal to 1, sure enough, this curve stops at n quantum well equal 1. For n max equals 3, again, sure enough, the curve stops here at n quantum well equals 3. That's the biggest it could be. So, as I say, take the first branch of the tangent function, n equal 1, that will be for the symmetric solutions, right? For the first symmetric solution. Let n max vary from 1 to whatever number, and track the intersections. Where does this intersect where do these two curves intersect as you vary n max as a parameter? Those are going to be the n quantum wells, that's this variable that you solve for, that satisfy at these discrete points, are going to be the values that you seek for n quantum well, from which you could extract your energy levels, right? So I went ahead and solved it for my, I mean, you got to do this yourself, of course. You're never going to get anywhere watching me do it. But here are my solutions for, let's see how I've labeled them. N quantum well, these are my solutions for n quantum well over here. For first the even or the symmetric case, and the anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric. And so if, again, n max is something you know. Have it on the next slide, for example. Let's just suppose that I have a well. Here's my conduction band. Suppose E1 infinity, whatever that number is, falls over there. And suppose I have the maximum potential energy of the well. I'm going to call it's called V0. Suppose it's 25 E1 infinity. Okay, so 25 above this, 25 times bigger than E1 infinity. Well, that tells me n max, because V0 is 25 E1 infinity, and remember that n max was the square root of V0 over E1 infinity, so that's the square root of, well, n max works out to be 5 then. It's going to be the square, V0 over E1 is 25, so the square root of 25 is 5, n max equals 5. Okay? Now, for n max equal 5, it's right here. So I draw a line up. Here's my first solution. I read across, and I find it looks like it's just under 1 for n quantum well, and indeed it's 0.886. Go up. There looks like there are 1, 2, 3, 4, 5 solutions in this well. oops, this well is deep enough that I could support 5 energy levels inside here before I hit V0. So the first one is 0.886 right here. This one, read over across. You know, again, you do this with a computer. Maybe 50 years ago you would have done this with a graph like I'm doing here, but no one does that anymore, right? That's 1.77. This point, read over, is 2.65. Read over here, 3.51. Finally over here, read over 4.33. So these are we see there are five energy levels in the well. I've solved not for the energy levels, but I've solved for n quantum well, but that's okay, because once I know n quantum well, now I do. It's these numbers I could solve for En infinity for myself. And that's what you need to do to make sure electrons' energy levels, as we're going to be spending a lot of time in the next several classes looking at energy levels in wells and what that means for making lights, optical sources, LEDs or lasers and so forth, or amplifiers for that matter. You need to know how many levels exist in the well and what those energy levels are, so you could have some assurance that the electron is well trapped in a conduction band. Otherwise, it's going to be a lousy laser. If the electron is not well trapped in this well, it could be free to get enough energy to escape that well, and you're wasting current is basically what's happening at that point. You're putting electrons in, you're injecting electrons, but you're not getting a corresponding photon. All you're getting is heat. And so, of course, that's something you want to avoid. Right? This all, as I said, is discussed in Appendix 1 in your book. Specifically, he gives, and I drew it here big for you. If you want to practice by doing this graphically at first, go ahead. He draws it a little bit differently. Instead of putting n quantum well, you notice how he does it. This is n quantum well minus 1, n quantum well minus 2, n quantum well, and you get a set of curves that look like this. Same thing down here for n max. This is, again, the Koldrin-Corzine-Manasevich text, figure A1.4. So I've reproduced it here for you. The smarter way to do it, of course, the sensible way to do it, if you have any, I mean, this is what computers are for, right? For engineers, this is sometimes I wonder if engineers think computers are for just Facebook and Instagram. You know, well, maybe that's entertainment. That's not technology. This is using the computer for technology. This is using it for scientific computing. I wrote a little routine in MathCAD. I like MathCAD for classroom use because it looks so nice. You know, I don't have to show you script from C or MATLAB or something. I get to show you this, you know, and it looks so this is everything right here. This is my little MathCAD script that gives me what I do is this is a calling function n quantum well as a function of n max. I put in my value of n max, it iterates for me and spits out the 5 values. Actually, you're seeing it spitting out 6 because if you look, is that a solution? Most people would say that was not a solution because that's when n quantum well is going to equal n max, and that means you have an electron that's sitting right at the very top edge of the conduction band. So even a little bit thermal energy is going to pop it out of there, and that electron's going to be gone. So nobody would accept that as a solution, even though mathematically it satisfies the equation mathematically, but my equation doesn't take into effect thermal noise that will change things a bit. So that's why there are 1, 2, 3, 4, 5 solutions in the well. And sure enough, where did I get these numbers that I typed for you here? I didn't use this graph. That's kind of the old-fashioned way to do it. Nobody does it that way anymore. You do something like this. You write a little MATLAB code or something like that. And here is how I got those numbers. It just popped right out. This is the simplest thing in the world. As we're going, it'd be well worth your while. Listen to me carefully. It would be well worth your while to write this little code for yourself. You probably like MATLAB. That's fine. And keep it, use it, have it handy to use, because as we move on and start to design lasers, we're going to need to know energy levels in the well, and this is where you get that from. Okay, this is where you get those energy levels. As far as the wave functions are concerned, once we have once we have the energy levels, we have our wave functions, and I wrote them out here really more for the sake of completeness. I think a little more telling would be the picture. There is the symmetric one, the first one, you notice has got the exponential deltas. Notice also for all of them how they're continuous. I purposely put in the boundaries for you here, plus or minus d over 2 with this dashed line. You notice how they're continuous at the boundaries, right? They've got to be smooth and continuous at the boundary. Not only you could see is no corners or cusps, right? That means not only is the function continuous, but its first derivative is continuous. So here's 1, 2, 3, 4. Here's the 5 wave functions for corresponding to these 5 values of n quantum well. Trust me, believe me, take my word for it, you must be able to do this. And you're not gonna, I can guarantee you, I've been in this business a long time, you are not gonna be able to do this by watching me do it. It's not gonna be possible. If I ask you to do something on a quiz, you're not gonna do very well if you don't do this yourself. So as a non-assigned homework assignment, what I would strongly advise, not even strongly advise you, what I would insist that you do is that you be able to draw these for yourself using whatever computer program you like. If you want to use MathCAD and you want to copy my code, I guess there's nothing I could do about that because I'm giving it to you. If you want to use MATLAB, if you want to use Python, if you want to use C, I don't care, but find some sort of way of drawing these curves for yourself. Make sure you could do them, make sure you could understand them. Am I clear on that? You get what this is very important. Okay. So a comparison here. Here's the infinite well that we looked at with n equal 1, 2. You could have an infinite number of energy levels in this well because nothing gets in, doesn't matter how high in energy you go. But once you have a finite well, I've shown one here, just one that where there's only 2 energy levels in the well. If there were a corresponding third energy level, the electron wouldn't be trapped in the well anymore. It would be outside the well. And the relationship, as we saw, for the infinite well is n squared E1 infinity. For the finite well, it's n quantum well squared E1 infinity. Now, what we're going to do is I'll probably stop here for this for this recording and finish up. We still have a few more slides to go through here, not too many, but let me tell you how you do this business, because it seems like it's very complicated, and in a sense it is. But what you do is you design your well using what we just did to make sure your electrons are well trapped, okay? And I'll even give you further, very soon, I'm going to give you further criteria for what it means that an electron is well trapped. I'm going to give you industry standard guidelines for people who make lasers. What do they do? I'll tell you what they do. You could design your well using these ideas so that the electron is well trapped. Once you know that your electron is well trapped, you can go back to the simpler infinite well case to do everything else, because you don't have to worry about electrons not being well trapped. You know that they are, okay? You know that they are. In other words, you know that you've made it so that, let's say, this first energy level or this second energy level is not sitting right at the top of the well, because then it wouldn't be trapped, okay? So once you've ensured that for yourself, and I'll tell you later, and I'll show you later, but I'll tell you the clue. The energy, the top of the well, this V0, has to be 5 kT above the Fermi level. You've had physics of EE, they talked about Fermi levels, I'm sure. You've got a Fermi level somewhere inside this well. You make sure that the top of this well is 5 kT above the Fermi level, your electrons are well trapped. That's where we're going to with all of this. And once the electrons you're confident are well trapped, you can move to this case and simplify your work. So we're going to stop here, and I'll pick up with another recording, finishing up these last few slides in our next recording that I'll post. Thank you.